Okay, for the next section for physics 3 exam review, we'll be looking at heat. So one thing that's important to realize is that heat is not the same thing as temperature. So temperature is essentially a measure of the average kinetic energy of all the particles. So if you increase the temperature, you can have one particle, you can have a million particles. It's just the average speed of them, you might say, like because it's their vibration energy. So that's why we say it's like a kinetic energy. Heat, on the other hand, is the total energy contained in the substance. So it's as if you were adding the kinetic energy of each particle together and you get a grand total. That would be your heat. So this is the total energy. So heat is total energy. Temperature is only the average energy. Okay, and we measure that in joules for the energy, that's total energy or heat. And for temperature, we use either degrees Celsius, Kelvin, or sometimes Fahrenheit. But we'll stick to Celsius for these problems. Okay, so how much energy is needed to increase the temperature of 5 liters of water from 12 degrees centigrade to 33 degrees? So one thing you have to know is what's called the heat capacity. So for water, it happens to be 4.190 joules per gram per degree Celsius. So that means that if you want 1 gram of water to have its temperature increased by 1 degree Celsius, you will need to add 4.19 joules of energy to that water. So we're looking at what we know. So first thing, we know that energy has to come from outside and go into the water. That's why there's an arrow going in. So that might be from a burner, it might be from an electric heater. It's just a source of heat energy. So that's going into our 5 liters of water. So we need to know how many grams because that heat capacity is measured in joules per gram per Celsius. So in this case, each liter contains 1,000 milliliters. So 1 liter equals 1,000 milliliters. And for water, it's really important to know that 1 milliliter is the same thing as 1 gram. It's also the same thing as 1 cubic centimeter, which we don't need to know for this problem, but that often comes up. For water, it's the weight, the volume in either cubic centimeters or milliliters is all 1. Makes it easy to remember. Okay, so since we started with 5 liters, and it's 5,000 milliliters, that means we know that we have 5,000 grams. Now the delta T is the difference in temperature. So we finish at 33, start at 12. We'll use a positive number for this. With energy, it's possible sometimes to use negative numbers if the temperature goes down, but we'll just talk about change of energy. We'll use a positive number all the time. So the difference between 33 and 12 would be 21 degrees Celsius. And the last thing we know is that 4.19 joules per gram degree Celsius. So there's a nice little formula for this. It's quantity of heat, which is represented by the capital letter Q, equals M, which is the mass of the substance that changes temperature, times C, which is the heat capacity, times delta T. Okay, so we use a capital T because the lowercase t is usually used for time, and the capital one is used for temperature. You'll notice that often the formula might mention that the degrees should be in Kelvin. That comes out to the same thing as a Kelvin degree is the same size as a Celsius degree. So those two formulas are interchangeable. If you look at tables, sometimes they will give you a value for kilograms. So if this was joules per kilogram degrees C, it would be 4,190. So make sure when you use the units are the same. Like the units you used in your problem and in the heat capacity are exactly the same. Okay, so we'll start finding the answer. So we have Q equals 5,000 times the heat capacity, which is 4.190. So the zero here tells us we have four significant numbers. For also the mass, we have four significant numbers. And finally, our delta T is 21 degrees C. And now we only have two significant numbers, which means we will have to round everything down to just two. So we'll use our calculator for this. So it should be around 210,000. So 5,000, oops, we'll turn it on first, that helps. Clear. Okay, so 5,000 grams multiplied by 4.19 times 21 degrees equals to 43,000, actually it's 439,950. So 439,000, just make sure, 950. Now, we had joules per gram degree C, which was the units for the heat capacity, and we multiply that times a gram times a C. So I'm just doing the units. So I can see that gram over C on the bottom cancels out gram over C on the top. I'm just left with joules. Now when I write the final answer, I have to round it to the correct number. So in conclusion, the heat is, I need two numbers, so 4.4. So I am rounding at the second one. Oops, I want to put this in red. Okay, so I'm rounding at the second one, and you will notice that the 3 is followed by a 9 because the 9 is bigger than 0.5. It makes it round up, so it's 4.4. Then I count the amount of decimal places. So it's 1, 2, 3, 4, 5. So that's times 10 to the 5 joules. You might also see it in kilojoules. In that case, it would be, this is another possibility. It would be 4.4 times 10 to the 2 kilojoules. So the K is a 10 to the 3 because it's 1,000. Okay, so we're done with this one. These are quite straightforward. Just find your values, find the formula, plug your numbers in. Now the second problem, this is where you have to do a bit of thinking. Like we start with a 400-gram porcelain mug at 20 degrees Celsius. So the mug is empty, it weighs 400 grams, and the porcelain itself is 20 degrees Celsius. So this is what we have in black on the picture here. This is the mug. And for the mug, M400, P equals 20. And then we have the heat capacity. That's way down in the problem. It says, assume that the mug has a heat capacity of 1.07 joules per gram degree Celsius. So we'll read the rest of the question. It says, what temperature? Oh, and then the second part, forgot the second part. Okay, the mug is filled with 1 imperial cup of tea at 80 degrees Celsius. So if we look in the assumptions, we assume that tea has about the same properties as water. It's very liquid, it's very dilute. So we have heat capacity of 4.19, same as water. And here we have m equals 250 grams. That's why a cup, especially imperial cup, is considered to be 250 milliliters. So that's about 250 grams. Same reasoning as in the number one. And then we're told it's 80 degrees Celsius. So what happens if you look at the arrow here is when you're filling the cup with water, the heat that's in the water goes into the portion of the cup. So we'll assume this appears, it makes a change very quickly, and that the heat doesn't go into the air, because around here we've got some air, and we can imagine that some heat would escape, but we'll say the temperature changes before any of this escape has time to happen. So we won't consider it in our calculations. So what's interesting is that if heat is going from the water to the cup, well, the amount of heat that the water loses has to be exactly the same as the amount of heat that the cup gains. So what we have is that the energy lost by the water has to equal the energy gained by the cup. So on the left here we have water. On the right here we have the mug or the cup. Okay, so we already have a formula for energy. So that's just Q equals mc delta T. So, but this is Q equals Q. So the Q lost equals the Q gain. So that's energy loss equals energy gain. So we have, and we'll use colors for this one. So it's the mass of water multiplied by the heat capacity of water times the delta T of water equals the mass of the mug multiplied by the heat capacity of the mug multiplied by the change in temperature in the mug. So in this case, none of these values are the same, but we know most of them. The only ones we don't know is delta T. Unfortunately, you have to realize that the change in temperature of the mug will not be the same as the change in temperature of the water, especially because the water has a much higher heat capacity, so it'll lose less heat to make its to change the temperature of the mug. Okay, so we'll write this out. So everything we know. So we know the mass of the water is 250. We know the heat capacity of water is 4.19 joules per gram degree Celsius. Now, the change in temperature, this is interesting. I will use a positive value on both sides. So we know that the water is cooling down, which means that its final temperature will be lower than its initial temperature. So we know it's going to be 80 minus T2. This is equal to, so I'll have to skip on a second line to do the second part. Move this over a little bit. Okay, for the second part, we're now talking about the mug. So the mug weighs 400 grams. The heat capacity is 1.07 joules per gram degree Celsius. And it's delta T, so here the mug will be warming up, which means that its final temperature will be higher than its initial temperature. Now, I want a positive value on both sides because I want positive energy. I want the energy to be same on both sides. So I'll put T2 minus 20. Now you'll notice I did not identify T2 temperature at the end as being for water or for the mug. The reason for that is that there's a thermodynamics law that says that once the temperature is the same between two different substances, the heat stops transferring. Heat will only transfer if there's a difference in temperature between two surfaces or two substances that touch each other. So in this case, we know that T2 will be the same and heat transfer will stop at that point. Okay, so now we'll do a bit of calculations. So we want to solve 250 times 4.19, and we'll also do the 400 times 1.07. Okay, so 250 multiplied by 4.19, so that gives us 1047.5. So 1047.5, and this is 80 minus T2. So I didn't touch the bracket yet. So on the right hand side, I'll do the same thing, which is 400 times 1.07. So we have 400 multiplied by 1.07. We get 428. So 428 T2 minus 20. Okay, from here on, it really is just like plain algebra. This would be like probably grade 10 level because you have a bracket and you have the variable on both sides. So you would have started learning this in grade 9, but by grade 10, you should be able to master this. So this will have to be distributed when you expand it. You have to multiply both same things. So I have to do 1047.5 times 80. So 1047.5 multiplied by 80. That gives us 83,800. So I'll just stick to black. I forgot the last part. So 83,800 minus 1047.5 T2. So we don't know what T2 is, so it's just a variable multiplied by a number. Equals. Now, we'll have 428 T2. That's easy. Now we have to multiply 20 times 428. We get 8560. Okay, so now I want all my numbers on one side and all my temperatures on the other side. So for this, still more algebra. So because t is positive on the right, I'll leave it there. It doesn't make any difference if you want it on the right or the left. So I have to do plus 8560 on both sides. And I also have to do plus 1047.5 T2 on both sides. So the reason I do this is the numbers on the right hand side become 0 and the T2 on the left becomes 0. I'm just left with my numbers on the left, so that's 83,800 plus 8560. So 92,360. And on the right hand side, I have to add those two also. So 1047.5 plus 428 gives us 1475.5. So that's 1475.5 T2. So I'll just get this line out of the way for now. And now we just have to get our temperature isolated. We need it alone. We have to remove that multiplied by 1475.5 by doing the opposite calculation, which is divide. Which means, according to our calculator, 92,360 divided by 1,475.5 equals 62.59. Now, before I write the final answer, I'll go look at my values. I'll notice that 20 degrees has two significant numbers, so I'll have to round that to the two numbers after the 2, followed by a 5, 9, which means I have to round up, and it would become 63. One little thing of note, if it was exactly 62.5, it would round to 62, because it has to be bigger than zero point 0.5 when it's an even number. When it's an odd number, it always rounds up. Okay, so here, in conclusion, look at the question, exactly how we have to answer. It says, what is the temperature of the mug filled with tea? So the mug is at 63 degrees Celsius. And that's how you can use heat capacity and temperatures to find the amount of energy, either the amount of energy necessary to change the temperature of one substance, or you can use the same type of formula to find out what the temperature is when you mix two different formulas. So all you have to remember is that there is a heat transfer, the amount of heat that one substance will lose. It has to be exactly the same as the amount of heat as the other substance will gain. And that makes the problem a lot easier to understand. Then the hard part with this is just the algebra. If you're good at math, you'll find this easy. If you're not so good at math, you'll struggle a bit, but as long as you have the theory right, you should get most of your points if it's a high school question.